Hello everyone, welcome back to BC Calculus. We're in lesson number 40 where we're talking about vectors. And in this very short video, we're going to talk about how to relate vectors to motion. So in the previous video, we talked about taking derivatives. And we said if we could take the derivative, we're taking the derivative of each function, each parametric equation, in terms of our I and our j. So the velocity is just going to be the derivative of our position function. So if I want to ask you guys to find the velocity of a function, given that this function is r of t, you just find the derivative of x, find the derivative of y, you're good to go. Skipping down here to the acceleration, you will find the second derivative, and that is very common, something that you've actually already done, and you know this very well. So this is just the first derivative, this is the second derivative, and again, you guys are very good at that. The distance traveled by an object, I love this equation because you've actually seen it already. So the distance traveled, again, these are parametric equations that you guys see here, and I'm asking for the distance traveled. So the distance traveled is going to be the whole song and dance, regardless if we're positive or negative. So if I go woo-shoo like that, I want the distance of this whole thing. So I'm positive, negative, positive, negative. So it does not matter if it's positive, negative, whatever. The point I'm trying to make here is that this is actually just the equation for the arc length of a parametric equation. And that's exactly what you guys have done before. So when you're asked to find the distance traveled of some vector, you're literally just looking at the arc length of your problem. The speed of the object is going to be, as you guys have learned back in particle motion, the absolute value of your velocity, And so I always tell students the easiest way to memorize this equation is to take the arc length and just get rid of the integrals. And it's the same thing. So these are very intertwined with each other with these problems. So let's go ahead and do these problems. And the only ones I think students need to kind of memorize is just this problem and this one right here. But again, you've already learned this one because this is arc length of parametric equations. And the speed, again, is just the absolute value of your velocity. So let's look at these problems, these three examples. It says find the velocity and the acceleration of a vector. So we're going to find that v of t is equal to, and yes, you could write, by the way, you could also write this. So r prime of t is equal to, so they're both the same thing, and you guys know that. S prime of t versus v of t. And so it's our derivative. So we're going to take the derivative of cosine, which is going to give us negative sine of t, and then we're going to leave our ion. And then the sine of t, the derivative of sine of t is positive cosine of t, j. So we can write it like this, and again, we can rewrite it as negative sine of t comma cosine of t. So there's our velocity function, and then our acceleration will be our second derivative. And I'm going pretty fast with this because I don't think this is something that students usually struggle with. So the derivative of negative sine is negative cosine, I, and then the derivative of cosine is negative sine, which we've actually done before. So we get negative cosine of t, and then we get negative sine of t. That is all you do, ladies and gentlemen, for these problems. So hopefully that makes sense to you guys, and we are good to go with that problem. So find the derivative for velocity, find the second derivative for acceleration, and again, it doesn't matter which one of these you guys decide to do, they're all going to be fine. Example number 2 says a particle starts at rest, so it tells us our rest of p of naught is equal to 2, 2, 0, and it moves with the acceleration given this right here. So we want to find the velocity function, we want to give you the position function, and then we want to locate the particle after 3 seconds. What's the location of our particle? So in order to find the velocity function, again, this is something that's not surprising for you guys. You know that you're going to be integrating this. So you're going to be integrating, 2i plus 6t j dt. It's going to integrate 2, which is going to be 2t with an I. And then, well, plus c, right? There's a plus c there. But I'll get to that in 1 second. And then you're going to do the integration of 6t, which is going to be 3t squared, plus c j. The reason why I didn't do the plus c here is because usually we'll give an initial value for velocity. It's okay, velocity of 0 gives you blah, 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 blah. But the question says that we're starting the particle at rest, which means that our velocity is actually going to be initially at 0, 0. So we're actually given that here. So the reason why I'm doing this is that, all right, well, 2t plus c1 is actually equal to 0. So c will be equal to 0, and then 3t squared, because these are polynomials. plus C2 is equal to 0, therefore C will be equal to 0. So I probably should have written that out just to show you guys, but if it's at rest, then you can just assume that this is 0, 0, and then plug in that way. So I knew the function was still going to be this function right here. So I hope that that makes sense. But the rest is telling you that v sub naught, the initial one, would be at 0, 0. We're not moving at all in these problems because remember, velocity being positive, moving forward or up, velocity being negative, we're moving down or to the left. So the position function, we're actually given values. So we are going to incorporate the C plus, the C1, the C2 thing. So the position, I don't know why I'm going back with the acceleration here. So my position function, which I'm going to call S of t, because that's what I like to call, it's going to be integration of 2ti plus 3t squared j dt. And so we're going to go ahead and integrate this as t squared, and then we're going to do a plus c1, and we talked about this in the previous video. And then we're going to integrate this, and we're going to get t cubed plus c2 j. And so we've actually said, like I said, we've already talked about this before, guys, the fact that t squared, and these are super boring because, again, we're at 0. So t squared plus c1 is going to be equal to 2. Well, this is going to end up being 0, so this will end up being 2. So I'm going to go ahead and erase this and make it 2. And then if I do, t cubed plus c squared, c2, and that's going to also equal 0, well, that's just going to give us 0. So I'm going to go ahead and make this plus 0, which obviously can just be what it's got to be here, but this is the idea for this. So our position function is actually going to be t squared plus 2 comma t cubed. And the reason why I write it like this is because part C is asking us to find the location of the particle at 3 seconds. So I want to know what S of 3 is. This is really awesome, ladies and gentlemen, because all you're doing here is you're going to take your function and you're going to plug in 3. So I'm going to do 3 squared plus 2, that's my I component, and I'm going to do 3 cubed as my j component. So I'm going to get 9 plus 2 is 11. And then I'm going to do 3 cubed is going to be 27. So this is going to be the position of the particle at time equals 3 seconds. So again, what this means is I've moved 11 units to the right, and I've moved 27 units up since our beginning. So let's move on to our last example of this lesson. And it says a particle moves in the xy plane so that we have the function the square root of 3 minus 4 cosine of t, and y equals 1 minus 2 sine of t. So these are parametric equations. That's the best thing that I can say about these problems, is that we have 2 parametric equations, so we can kind of relate these things to what we need to know. It says the path of the particle intersects at the x-axis twice. All right, so that's important for us to figure out what to do with that. Find the distance traveled by the particle between the 2 x-intercepts. So this basically is a FRQ that has to do with a little bit, really no vectors, honestly. It's more of a parametric equation problem, but it was part of this FRQ, so I'm going to go ahead and talk about it because I think it's really awesome. So first of all, let's look at the x-intercepts. So it says it intersects the x-axis twice. So what does that mean? Well, if it intersects the x-axis twice, that means y is 0, right? Y is 0. On the x-intercept, y has got to be 0, wherever it is. So we're going to take our equation and we're going to set y equal to 0. So we're going to set 1 minus sine of 2t, 1 minus 2 sine of t equal to 0. I promise you guys, I know what I'm doing here. So we're going to move the 2 sine of t over, and so we're going to get sine of t is going to be equal to 1/2. So we know there's 2 places where sine is equal to positive 1/2, in quadrant number 1 and in quadrant number 2. So those are going to be our intersection points. Those are going to be when it says find the distance traveled, which again is going to be the arc length, right? We're looking for the arc length of our function here. We're going to actually do this. So that's really what this question is asking us, is finding the arc length. So we're going to go ahead and integrate from pi over 6 to 5 pi over 6. So one of the next things we have to do is we have to do square root with our dt, and so we have to find the derivative of x, and we have to find the derivative of y. So we've done this in the previous lesson, or a couple of lessons ago actually. So dx dt is what we're going to put in right here. We're going to take the square root. Well, the derivative of the square root of 3 is just going to be 0. So we're going to take the derivative of negative 4 cosine of t, which is going to give us 4 sine of t. And so we're going to plug this guy in as 4 sine of t quantity squared. And then we're going to find dy dt, and that's going to be the derivative of this. Again, the derivative of 1 is 0. Derivative of negative 2 sine of t is negative 2 cosine of t. So we're going to do plus negative 2 cosine. And again, all I'm using right now, guys, is the formula for the arc length, which actually is written up here for us as well. So it's the distance traveled of our particle if we were in vector form. So there we go. And we could absolutely make this problem easily a vector form, and I'll talk about that one second. So this is in our calculator. So we're going to plug this into our calculator, and you're going to get, this is going to be 7.347. So this would be the answer to this problem. So knowing this is the arc length. But I think the hardest part here may have been just to figure out, what our bounds were. But so there's always something. If they don't give you the bounds, it's not 0 to 2 pi. And students will always do 0 to 2 pi here. Read the whole question to make sure you understand everything that's being given to you. You guys could see this as a function. So I could say to you, looking at the function, that some value of r of t would be equal to negative 3 minus 4 cosine of t j, or I, excuse me, plus 1 minus, and let's put parentheses around this thing. So plus 1 minus 2 sine of t j. And so we can then rewrite that in terms of x and comma y. Well, our functions that we would have. So that's our vector video for you guys. I hope that this all kind of makes sense, and I will see you guys in the next video. Take care.